Hi there, and in a sense, welcome back at British Columbia Institute of Technology's TTED 4044 course. And this is the second part of this week's lecture. The previous part, you may have just seen, we were using a compression testing jig to do compressive testing on thin little samples of MDF for the laser cut truss that we're going to be designing in the next week or two. And I wanted to give you a little bit of background on some of the theory, because one of the things that we noticed when we were taking those measurements, somewhere I've got my measurements right here, is that when we cut the length of a member down in half, and we had a little chart like this as we were plotting everything out, and we were recording our data on a table like this, we noticed that the 150 millimeter long member was 4 times as strong as the 300 millimeter member of the same cross section when we loaded it in compression. And that's a really interesting thing to note in terms of the Euler buckling formula. And what's useful to note is that this is also very closely related to beam bending. So when you go on to Desire to Learn, and well, if you're taking the BCID course, you'll have got access to Desire to Learn. If not, you'll see some of the notes here today. But I tend to talk about column buckling and beam bending at the same time because, well, really, when you bend a beam this way, okay, you're really dealing with the overall stiffness of the beam, and that's an important factor. Well, when you buckle something this way, you're also dealing with the stiffness of this column. Its resistance to popping out to the side is the same as the resistance of a beam to bending down this way when you put a load on it. So column buckling and beam bending have a lot in common. Now, right now, because we're talking about trusses, we're not talking about bending moments or anything like that because everything is a pin joint, so there are no bending moments. Later on, we'll come back and we'll talk about beams where that is a big factor. But right now, I'm going to take a look at how some of these formulas apply to column buckling. And you'll see on the handouts that I'm also talking about beams on the handout. Don't worry about the beam stuff so much, but we're going to take a look at some of the important parts of our formulas right here. So on Desire to Learn, if you're enrolled in the class, you'll find 2 sets of handouts, and there's one that says at the top, structural properties, beam and column buckling, and the other one will say beam and column buckling part 2. Yay, more. So anyway, let's just take a look and go through what I typically do as the lecture related to the handout on beam and column buckling. And we start out by talking about what is a material property versus a structural property. And we spent our first semester in our material science and structures program here at BCIT taking a look at material properties. So we looked at tensile strength. And tensile strength was very much a material property because it really didn't matter how you shaped your tensile test specimen. The more material you had, the stronger it was. So you had no advantage in tension from going to an I-beam shape or a hollow shape or a cylindrical shape versus a cross section. Theoretically, in tensile, all that matters is your cross-sectional area. But when we start talking about beams and columns, structural properties start to become really important too. So if we take a look at a structure made out of steel, for instance, an I-beam or a column made out of a hollow steel cross section is going to have different properties than one that's made out of a solid steel cross section, even if they have the same amount of area. And you know this from looking at things like rulers. You've all done the thing where you put the ruler on the side of the desk and you go, oh, is that coming through? Twang. Yeah, I can't do it for you right there, but the twang that you get that way. And then you flip it on its side like this, so you're looking at it from the height wise, and there's no twang, there's no fun right on there because that's it's not flexing. And we know that this is way more flexible in this direction than it is in this direction. And of course, if we load it in compression, we know which direction it's going to buckle in. It's going to pop out to the side in the thin cross section. Well, there's good engineering reasons for this, and there's great formulas that explain exactly how it goes. And as we saw in our previous video where we did some compressive testing, even with very rudimentary equipment, we can observe those relationships showing up in the materials that we test. Okay, and one of the things that we're going to talk a lot about when we start getting into column buckling and beam bending is Young's modulus. Okay, and Young's modulus, you'll probably recall from last semester, is also known as the elastic modulus. And what it does is it tells you how far something will stretch under a given amount of stress. So that's a material property that's really, really important for the structural properties related to beam and column buckling. And you'll see that showing up time and time again. Now, um, this gets into beam bending and how it bends. And we talk about ways that we can make a beam light and stiff. Now that sounds like a pretty abstract question until you start thinking about things that really matter in everyday life, like hockey sticks, okay, and golf clubs and tennis rackets and bicycle frames and all of those things that are really important to us because we want our hockey stick to be light and stiff so that when you wind up and take a hard shot, that it flexes just the right amount for you. Sometimes the stick might be too stiff. So the stick that Zdeno Chera uses is not the right stick for me um, because if you've seen my slap shot, the stick that your 5-year-old nephew uses is probably about the right stick for me, maybe a little bit longer. Anyway, so beam and column buckling, the stuff that we do right here has really applicable outcomes, not just in terms of buildings and structures and cars and things like that, but in terms of bicycles and laptop cases and how your phone is put together. This is getting into the real nitty gritty of how real world structures bend, flex, and break. So let's flip the page over right here. And I'm going to go through this pretty quickly because we'll probably come back to it again if we get a chance to talk about beam bending a little bit more. But let's just take a look at that question about why was our ruler so much stiffer in this direction than in this direction right here. And that's got to do with the fact that when we take a look at it right here, in order for it to bend, okay, and I've exaggerated it a little bit on this diagram, but in order for it to bend, everything on the top goes into tension and has to stretch to a new length right here. And everything on the bottom gets placed into compression. And so when you think about that, that's going around like there. This was the original length right in here. But after we stretch it, the original length was right here. This is all stretching. And this is all, well, it's stretching too, but it's stretching and compression. It's being pushed together. Okay, so tension and compression are really, really important in the bottom layers behind what's going on in our beam bending. Now, the reason that the shape matters so much is that if this side of the structure is in tension, and this side of the structure is in compression. So if you're pulling on the top and pushing on the bottom, there's actually a line that runs right through the middle of the structure. Now, depending on what the cross section of the structure is, you've got this line right here. Well, out here, your highest tension. In here, you're at your highest compression. As the tension drops off, and as the compression drops off, because they're the exact opposite of each other, at some point you need to transition from tension to compression. And that point is actually not stressed at all. That point in the middle is the exact same length that it was when it started out, and it's not stretched and it's not compressed. So really, that little line, if you break your structure down and say this beam was made of a whole bunch of rulers put together and you went to bend them like that, the ruler that was right in the middle would be reasonably unstretched. Okay, so it's a neat way of thinking about your materials as they come together. Now, obviously, if a material is thin, okay, this way, then the difference in length between the top and the bottom is pretty slim. Okay, so it's easy to stretch it like that because you don't have a lot of change in length on the top or on the bottom. You don't have a lot of tension or compression happening. You can go quite a long ways with that. But in here, to get this to bend anything more than the tiniest little bit, okay, this part needs to have quite a big change in length, and this part down here would also need to have quite a big change in length. So when you put that up vertically and you press on it like so, of course it's going to pop out to the side because that's the easiest thing for it to do. Now, because the shape matters so much and because the material in the middle is doing very little to resist that buckling or that bending process, and the material on the outside is where all the work is happening, we have some formulas that help us say, did you put the material at the outside where it can help you, or did you put it in the middle where it's pretty much useless? And the term used for this is, I'm going to call it the moment of inertia. Uh, more correctly, it's the second moment of area. Okay, um, it's a calculus thing. We don't need to get into it, but that's a better term for it. But we'll call it the moment of inertia. And this is our bending moment of inertia. It's different from the moment of inertia that you calculate for figuring out how things spin and rotate. Okay, but anyway, moment of inertia. We're using I, and you can find discussions online where people will argue whether we should use, say, second moment of area or not. So what we're going to do is on the next page right here, we take a look at two different types of cross section that we can use for this. Now, if we were studying engineering, and if we had a big background in calculus, you can sit down and you can go through and you can calculate where this formula comes from. In fact, there's YouTube videos out there if you want to know bending moment of inertia. Go ahead and Google that. There's some great explanations of how they go through and they calculate each tiny little infinitesimal cross section. You add up an infinite number of tiny little cross sections multiplied by how far away they are from your central axis and where it comes from. But we can take all of that hard work and we can take all of that math and we can sum it up into two formulas that are worth knowing. And then we simplify them a little bit more too. And so for a rectangular cross section, which when we're laser cutting our samples, everything's going to come out rectangular, we have a formula that says the moment of inertia is equal to the base, okay, multiplied by the height cubed divided by 12. Okay, and if you're dealing with a round cross section, which we're not at the moment, it would be pi r to the fourth divided by 4. The derivation is quite interesting, and I do encourage you to watch the video. And it might, if you haven't studied calculus before, it might make you realize that the calculus formulas are as beautiful as anything you'll find in any art gallery. Um, It doesn't sound that way, but just as you need to understand the art to appreciate its beauty sometimes, you need to understand the calculus to appreciate its beauty. And calculus is amazing. Even though I didn't always pass the course the first time around. So let's take a look at this. And we're going to ignore the circular cross section until later on, because when we're talking about our samples and the things we test in the lab, they were all rectangular, and we're going to be very applied and apply this formula just to the rectangular things. Now, anytime you look at an engineering formula, or any formula for that matter, and you're trying to figure out what is the most important part of the formula, look for the exponents. Okay, if it's a squared function, it's important. But if it's cubed, it's huge. And in here, you can see that we have a cubed function. I equals BH cubed on there. Okay, so H, when we're looking at our members right in here, okay, is the direction of the force. Now, in a beam, we can control the direction of force and we can stack something up tall. Okay, okay, so in a beam, I can say, am I going to load it this way or am I going to load it this way right here? Okay, but in a column, you don't get that choice because in a column, you're just loading it from the ends. And when you push down on it, it will always fail in the weakest direction first. So for our column buckling, H is always the smallest direction. I've drawn it as the tallest one here because in beam bending where you can control it, you always want H to be the tallest because it's got that cube after it, which makes it hugely, hugely important. Well, in column buckling, H is the smallest dimension. Okay, so if I was looking at this ruler and using it for column buckling, then it's this dimension right here, this puny one that's going to be my H. This one out here is just going to be my B. And if you look at that, the B, okay, your big dimension in column buckling, doesn't have an exponent there. That means it responds linearly. You double your B and you double your resistance to buckling. But if you double your H, your smallest dimension, and you make that twice as big, that's got a cube after it. So your member is now 8 times as resistant to buckling if you double the smallest dimension. So huge impacts on changing the smallest dimension when it comes to column buckling. Now, of course, for a cylinder, which we're not talking about right now, there is no smallest dimension. It's the same all the way around. And so that's why you actually get a fourth in there, a fourth power. Absolutely massive importance. You double the radius on a cylindrical column, and you get a 16-fold increase in its the amount of force that it's going to be able to resist before it buckles. Really amazing stuff. Now, there's some questions that go through here. We'll come back to those questions later on when we take a look at beam bending. But let's pop over right here. There's some beam bending formulas on there. And again, you can see, anytime you're looking at a formula, just look for the for where the exponents are, and that will tell you what really matters. So in this case, just as we had a cube in the moment of inertia calculation, you'll see there's a cube in the beam bending calculation. So the length is really important in beam bending. If you double the length, its deflection increases by a factor of 8. And we're going to see something similar to that when we take a look at column buckling. And the rest of this handout goes through and it talks about what do you do if you have hollow cross sections and why are hollow cross sections so important. In other words, why does that carbon fiber hockey stick that is made in a place that's never really heard of hockey do a better job than good wooden hockey sticks made in rural Quebec? Well, because good wooden hockey sticks are all solid, and you can get big advantages by going hollow. Anyway, we can come back to that if we get back and do some more stuff on beam bending, but right now we're mainly looking at column buckling. And so let's pop over to our second handout, because buried in the second handout is this little section on column buckling, which is something that I want to take a little bit of time to talk with you about today. Now, it goes through and it explains it in more detail, but we've got this neat little chart right in here that I've stolen from a website that probably stole it from a textbook, that probably stole it from a paper that was probably, you get the idea. This has been around for a while. The concepts are known far and wide in engineering. And what this shows you is that we've got different ways of loading a column in compression. Now, since we're making a truss, we're going to assume that everything is pinned top and bottom. And this is a reasonable assumption based on the testing that we were doing, because you'll notice that when we tested our samples, they were free to swing like this at the top and the bottom. Now, as you got into some of the wider samples, they might have been starting to approach a situation like this where they weren't free to pivot about their ends. But by and large, we were testing pretty small samples, and if they wanted to pop out to the side, there was nothing securing them right in there. You can also get situations where they're secured at one end, and what this means is basically that's being held at 90 degrees while this one is free to rotate. Or you can get situations where they're secured at one end at 90 degrees. So you put a post in the ground or a flagpole in the ground, and how much weight can you put up on this end? Well, that's free to flop over either side. And then you get ones where rollers start coming in, and we're not looking at that. 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 We're looking at this one right here. Okay, and there's our formula right there, pi squared EI over L squared. Okay, now, sounds great. Yeah. Usually I get to this point, oh yeah, pi squared, EI over L squared. And someone bumps the person next to them in the lecture and just says, just smile and nod, it'll be over soon. And anyway, it's not that hard to understand. Okay, E. That's the elastic modulus that we studied last semester, and I told you was going to be important in how things respond. Now, that's a big deal if you're trying to choose a material to use for your columns. But since we're making our trusses out of MDF, you don't get to choose that material. It doesn't change. So that effectively becomes a constant in your equation. Okay, just like pi. Okay, pi, it might be squared in here, but who cares? Unless you've figured out a way to change the value of pi, you can ignore that number. It just all gets worked into a constant somewhere. You can't change that by changing your design. And if you do figure out a way to change the value of pi, let me know. I'd love to have my name on that paper. So we can ignore that, and we can pretty much forget about that, because yes, it matters if you're calculating an absolute strength, but it doesn't matter if you're calculating a relative strength. And we're going to spend a lot of time looking at relative strengths of how one column compares to the other. Same thing, since we're not changing the material, okay? We can't adjust the elastic modulus of the material. That all gets rolled into a constant, and we're left with two important terms left over, the moment of inertia and length squared. Okay, you'll recall that when I had a long section of MDF, it failed at about 5 newtons. And when I cut that in half, it failed at 20 newtons. It was 4 times as strong when it was half the length. That's that squared factor, okay? As we increased the length, and as we doubled the length, that went from 1 over 1 squared, which is 1, to 1 over 2 squared, which is 4. The one that was twice as long was 1/4 the strength. Okay, so that's what's going on right in that beautiful diagram that we've stolen from this website right here. And we've just said that you could ignore 80% of that. And then within the 20% that we were looking at, I just said, because you can't change the material and you can't change pi, we can ignore those parts too. Let me zoom back out a little bit so you can see the whole page. Okay. Now, down here, we talk about the force that a column can support. Now, when I said you ignore all of those, that's because you can't change them. So you can take all of these things that you can't change and roll them all together into one constant. Okay? And that constant value will be the same so long as you don't change the material, which controls for the elastic modulus, and you don't change pi, and you don't change your loading conditions that we talked about right up here. So everything in your truss is going to be pinned. You can't change that. So you can't change the K, you can't change pi, you can't change E. So just forget about all of this. when you're calculating your formula, focus on, we can say that approximates I over L squared. Now, what have I got on the next page here? So I'm going to stick with this for just a moment right here. When I talk about I, well, what do I have for I? We're dealing with a rectangular cross section. So I, let's expand that out a little bit, is going to be BH cubed over 12. Now, for relative strengths, okay, you can't change 12 either, so let's get rid of that. And so for our relative strength of a column, is proportional, okay, to, proportional is a triangle, I think. I'm using the approximate, but bear with me here, to BH cubed over L squared. Now that's not the full formula, but it tells us the things that we need to know. And when we take a look at that BH cubed over L squared, H cubed, this is the smallest dimension of our rectangular cross section. And B is the larger dimension. Okay. And so in this case, we're going to be able to take a look at approximately how the strength of two different columns compares. Now, we took some readings and we got some data. We plotted them on a chart. And let's take a look at how this applies to the ones that I got some actual data for. So right here, our 300 millimeter long column came in at 4.83 newtons. And I made a prediction that the 150 millimeter column was going to come in at about 20 because it's half the length of the 300 millimeter long one. So let's just take a look and see where I got those numbers from. I wasn't just pulling them out of thin air. Find a blank sheet of paper to write on here. There we go. So if I know that this column strength is proportional to, where did I write that down? There we go, BH cubed over L squared. Okay, and I'm testing columns of the same cross section. Okay, then I can't play with my B and my H. So the only thing that could change would be L squared. So if I said, okay, my first column is going to be, well, I had 300 millimeters. For my L, okay, and my strength was 4.83 newtons. And then 150 millimeters, and I wanted to know what that force was going to be. I take a look at this and I say, well, what's the ratio between these two? 300 divided by 150 millimeters is 2. Okay, so my 300 millimeter one, if I put 2 into the L squared right there, is going to come out as a factor of 4. So I said, well, this is pretty close to 5. I multiplied it by 4. Really what we'd be getting here in our calculated value is going to be about 19.6 or something like that coming out there. And what we ended up observing was that it came out at 20.1 newtons, which was pretty good. This leads me to think that if I needed to figure out how strong would be a 200 millimeter column, let's do the comparison between 300 millimeters and 200 millimeters. Okay, right in here, that ratio is 1.5. And if I take 1.5 squared, okay, that's a factor of 2.25. So I would expect my 200 millimeter column to be 2.25 times as strong as the 300 millimeter column. So let's see how that works out. If that equaled 4.83 newtons, and this one, because it is 2/3 the length, okay, a ratio of 1.5 right here, then I'm going to get 2.25 as my ratio, and I can take my 4.83 and I can multiply by 2.25. And let's see what we get coming out there. 4.83 times 2.25 equals 10.86 is our predicted strength for 200 millimeter long. And so that's pretty close to 11, and I ended up getting 12.4. And that's accurate to close enough for me. Okay, pretty much 11. We observed 12, came out a little bit higher. Uh, Keep in mind that I only had one set of data to work from. I didn't go back and test multiple samples. So if we'd done 100 samples, then randomness in the testing procedure would have started to work its way down. Now, where that comes in handy is that you might be designing a truss, okay? And you might go through and use software to calculate your truss. And maybe there's a member down here, and that says that that truss, member of your truss, has to be 12 centimeters long, or 120 millimeters, okay? And it's going to be subject to a force in compression of, let's say, 30 newtons. And we want to know how big do we make this member right here in your laser, because you're going to design this and you're going to want to know how wide do I cut this member right here. Okay, so you can come into your chart right here and you can take a look, and it might just happen that for 12 centimeters you've got a reading, okay, and it says that, well, if you make it 4 millimeters by 3 millimeters, okay, then you're going to maybe be a little bit too strong, okay? Because you're going to be trying to make the truss as light as possible. You can definitely make your truss 4 millimeters by 3 millimeters. We know that truss can that member can withstand 30 newtons. But could we make it thinner? Could we go to 3 millimeters by 3 millimeters? Now, one way to know that for sure is to do a test and get your data. But just as we were able to adapt for the length in here, we can also adapt for our thicknesses, and we can predict pretty accurately what we're going to get as a result. Okay, now keep in mind that my 4 millimeter sample was actually 3 point, we'll figure out what the thickness we want it to be right here. Okay, that's what we're trying to calculate. When we took our data, our cross section of the member was 3 millimeters by 3.86 millimeters. Okay, it wasn't exactly 4 because of the kerf lost to the laser. And when we get down to this size, that might start to make a difference. But let's see what would happen if we cut some, let's see how big we'd have to make it in order for this to come out. Now, you can calculate the moment of inertia for this. In fact, you don't have to calculate the whole moment of inertia. You just need to say BH cubed, where B is the smallest one, so that's going to be 3 millimeters times, B is the largest one, so the H is always the smallest one because it always fails in the direction of H. So that's going to be 3.86 millimeters times 3 millimeters cubed. Okay, and so if we take our trusty calculator out and say 3.86 times 3 to the power of 3, I get 104.2 millimeters to the fourth. We probably don't need that 0.2 in there. Okay, now I know that this cross section in 120 millimeters can support, and I got this data off the chart right here, 120 millimeters can support 42.6. Okay, I need to support 30 newtons right here. So what I can do is I can say, if I need to support 30 newtons, so let me switch pens right here. This will be a bit more, is that more visible? 104.2 millimeters to the fourth is 42.6 newtons. Okay, I need to support 30 newtons, so I need to have a moment of inertia that's less than 104.2, so I can figure out my ratios and say 42.6 divided by 30, so I can come down by a factor of 1.42. Okay, so 1.42 between those ones, so 104.2, 1.42 gives me 73.4 millimeters to the fourth, should be able to support 30 newtons at 120 millimeter length. Now, I know that my formula for that came from BH cubed. Now, in this case, our H was the 3 millimeter thickness, so let's leave that set to 3 millimeters thickness. So that gives us 27 right there, okay, because 3 millimeters to the power of 3, 3 times 3 is 9, that's a squared, and then you cube it, 3 times 3 times 3 is 27. Okay, so it's going to be B times 27 equals 73.4. So 73.4 divided by 27 gives us a thickness of 2.71. Now this starts to become a little bit dangerous because the 2.71 is slightly smaller than 3. So this would now actually become our h cubed term over here because it would most likely fail in that direction first. But it's close enough that maybe we just round that up to 2.8. Let's see, can 3 times 2.8 cubed to the power of 3 equals 22 times 3. 2.8 doesn't quite do it. 2.9 cubed times 3 comes out to 73.1. So I would say about 2.9. I shouldn't have put that right there. 2.9 millimeters times 3 millimeters is going to give me the thickness that I need. To support a 30 Newton load at 120 millimeters. Okay, so it's a very simple way, sorry about that, I slid off the screen, very simple way to take a look at very complex formulas that have been derived for us using calculus and say, how can we apply them in a meaningful way? Okay, it's like saying, you know, if I've got one ice cream for every student and I've got 10 students, I should probably get 10 ice cream. Okay, that's just a ratio. In here, it's just a ratio, but there's a squared factor involved. And it doesn't make it any more complex. You just have to punch the squared factor in and consider that as part of your calculation. It's different because humans don't tend to think in exponentials. We don't visualize the world in exponentials. But when it comes to column buckling and beam bending, the length is a matter of a squared exponential, and the smallest dimension is a matter of a cubed exponential. So things get really important when you start putting those squares and cubes in front of them, but you can still use them to calculate your formulas. I know it doesn't make a lot of sense right now. Not everybody. Will come back. We'll do it a couple of times, and you'll start to see that you can use this to make reasonable predictions on how thick your members should be. In this case, I said, well, we're stuck with a 3mm thickness because that's the thickness of our MDF, so I can't play with that number too much. But when I come to cut it out, I want it to be 2.9mm right in there. Okay, looking at it from the side, so my laser will cut something out to 2.9. And what I want to do to get that is I'll probably draw my lines just 1/10 of a millimeter off on either side to account for the kerf. And so I'd probably space them by 3.1mm and have pretty much the perfect member to support exactly the load that we predict is going to be on it. Now, if you're designing a real bridge that people are going across, add a safety factor. But for what we're doing, go for it. Thank you very much, and we will talk more about this. I guarantee it.